We're going to have some talks from some of our grad students. Alexa, Chris, and Keyan will be talking about their research projects. And go ahead and take it away. Yep, Alexa.
Yeah, all right. Hi, everyone. My name is Alexa, and I am a third-year PhD student here at the IfA. I'm originally from Hawaii, but I went and did my undergraduate and got a degree in astrophysics from Yale University. I've since come back and completed my master's here, and now on to the PhD part. So I'd like to share a bit with you folks today about a project that I did as part of my master's, where I took a swift multi-wavelength look at the Dipper star EP Chamaeleon. So I can just dive right in. So the main focus of my research in general is looking at the process of how planets are formed. And so to give you a bit of context as to what this generally looks like, first, we typically start with a huge cloud of gas and dust and other interstellar material that's kind of just blobby and floating around out there in space. Eventually, though, because these clouds are so massive, they will start to gravitationally contract in on themselves. Therefore, you go from a cloud to something that is then collapsing in on itself. You can see material streaming into the young star that's forming. You can see some material starting to orbit the star that's forming. So everything is really hectic, really chaotic. But eventually, as millions of years begin to pass, this material will condense down into a disk around the star. So now instead of this huge amorphous cloud, you have a disk of gas and dust that is around your young star. And we think that it is from this disk that exoplanets, comets, and other interstellar type of bodies, like the asteroids that Larry was talking about. This is probably the material that they originally form in. Again, you let another couple million years go by, and finally you are left with something that looks like our solar system today. And so again, quick recap, we have cloud, we have collapse, we have disk, and then we have solar system. So the main focus of my talk is going to be on this step here, where we are looking at the disk that planets and other bodies are forming out of. This here is actual data taken from a radio telescope in Chile of these protoplanetary disk type objects that I've been talking about. And as you can see, they are just spectacularly stunning images. You may notice that there are some rings and gaps that seem to be carved out in some of these disks, and those are thought to be formed by planets that are inside of those disks, clearing out their orbit of debris, making it so that they can continue to orbit the star nicely without perturbations. So these are the types of observations that we're able to see. We're able to see planet formation happening in real time. However, we can see it happening on sort of a large scale. But how does this convert into the scale that we think of when we think of, say, the solar system? Here is an image of a disk that was one of the many in the panel shot that I had shown previously. And we might want to think about how big the solar system is in contrast to this disk. And if we look, this black circle here shows about how large the solar system is in comparison to the observations that we're making. So we're able to see planet formation happening way, way out on the outskirts of very massive disks far away from us, but it seems like we can't actually get down in and resolve the region where planets like our own Earth may have formed. And so if we can't just take a picture and be able to see these processes, we should try to figure out other ways instead that we can observe this region where planets are forming. Now, there are three reasons why this is hard to do. First of all, as you can see from the previous image that I had shown, it's really hard to get down and resolve structures that are that small. Secondly, disks are not actually completely flattened disk shapes. Instead, they can have flares and warps. And these are what you see here. These are 3D maps of a sample of disks that are taken. And you can actually see that they have, curves, they have rising profiles, they have dips in them. And so there's a whole bunch of geometric effects that could be obscuring this very, very middle inner part where planets are forming. This here is an artist's rendition of what it can look like when a star is then pulling material from the inner disk onto itself in order to feed and get bigger and bigger. This process can also induce some geometric effects that we observe from the ground. As you can see, the material is physically lifted up out of the shallow disk in front of maybe an area that is unobscured that we can see, and then back down into the star. So this could cause stellar occultations or essentially block starlight that we would see. these objects that we have, where then we see these dips in brightness, we aptly have called dipper stars. And this is a quick, more characteristic cartoon of what you may see in a science type of paper. This here shows that same disk with some material coming up and flowing in onto the star. And this schematic here shows material that may be driven by a stellar wind or a disk wind, may pick some material up, throw it in front of the star so that we can't see it anymore, and instead we see this dim signal. Even though it may sound like an issue that we are obscuring our star in order to make observations of our disks, what this does is it actually allows us to characterize the material itself that is between the star and us, allowing us to further understand the types of material and dust and gas that goes into forming planets eventually. For my project, I chose to look at one specific star, Chamaeleon. And this here that I'm showing is called a light curve. Basically, you take the brightness of the star and you look at it over the period of, say, 100 days. And what we can see is that there's some type of baseline brightness that IfA has, but there are these very regular dips that are happening. We think that these dips are either due to those clumps of dust that are being thrown up in the air or from material that's falling down and accreting onto the star itself. So this is what the type of data that we're looking at is like, since we're no longer able to use those really beautiful images to get down to the scale of science. IfA, in addition to being a dipper star, is a really good place to study the inner planet-forming region of disks because of its environment. It is located in a cluster that has other similarly young stars that are just starting to lose their protoplanetary disks, and so there are probably planets that are left inside, and we want to be able to see them. This here is a Hubble image of the Chamaeleon cluster, and I just wanted to take a minute. You can zoom in with this little box here. And if we blow this box up, this is the type of data that I was working with. And if we then zoom in just a little bit more, that finally is our target. This here is IfA from very, very far away. Now, we decided to take observations of our target with a bunch of different instruments that spanned a range of different wavelengths of light. And we did this essentially to try to probe different types of material that is in the disk. So here is a crosscut of a disk that I have shown here. Out here you have the outer disk, which is essentially a mass reservoir. As you move inwards, you start to form planets. Then your dust starts to drop away until you just have gas. And finally, you have this little accretion stream that I had talked about before. So our big, beautiful images of protoplanetary disk that traces the region that's out here, and this corresponds to this in this figure. We then go and we draw our little solar system bubble, and that corresponds, roughly speaking, to about this value here. And now we can start talking about the science that I actually got to do. First, we looked at the dust grain properties of this material in the disk, and we used light curves here, similar to the one that I had shown you before, and this was able to probe dust grains of a very specific size. Moving inward, I then was able to design a pipeline for use with the Rapid Eye Mount telescope. And we created this to compare to other space telescope observations. And so you can see the blue points are the pipeline that I wrote. The curve in the background is from a space telescope. And so based off of this, we're able to probe slightly larger grains of dust. And we're able to see that the method that we're using seems to be agreeing with what other people have done, which is exciting. From here, we want to begin to trace maybe some of the gas properties in addition to the dust. And we can take observations in the X-ray of our star, and we can fit different models to it, which is what these curves are, to estimate how much material is physically blocking the star from the disk. Last, what we can also do is we can look at the gas that is furthest in to the disk. And this is material that's being accreted onto the star from the disk. And the width of this line here corresponds to how fast and how much material is falling in. And so putting all of these different types of observations together, from this, we can estimate that the star IfA is only gathering mass at a very, very weak kind of rate. In addition, we see from most of our observations here that the dust grains within the disk of IfA seem to be relatively small compared to other planet-forming regions. And last, from our X-ray data, we detect a lot of gas and not a lot of dust. So putting these things together, we are not seeing many dust grains, any large dust grains. This is probably because the dust has already been pulled together to form planets that is within this inner disk. And that's why we're not seeing dust here, why we're only seeing teeny tiny dust grains over here. We also know that the star is only weakly gathering mass, so something is probably blocking those influxes of material. Again, pointing to the sign, there is potentially an embedded planet somewhere within the disk. And as time goes on, it'll take another couple million years. But as that happens and as the disk dissipates, we may finally be able to understand if there was a planet that was causing some of these perturbations and features here. So thank you so much for your time, and I would love to take any of your questions. Thanks. Alrighty, thanks everyone.
Did you have a question?
It's
yeah.
a more general question and sort of not really. So the initial gas cloud is a 3D gas ball. Is it? Why is it that a lot of planets seem to show like a disk rather than a 3D sort of
like a ball?
Yeah.
So I feel like there are two main sort of shapes within astronomy: balls and disks. And the other grad students over here are nodding at me. So basically you have your big clump of material that's condensing down in, and as this happens, you're going to have individual particles that are knocking into each other, slowing each other down, pushing each other in different directions. And so the only way that you're going to have material that's remaining sort of coherently bound is if you have material that is not necessarily canceling out in terms of the direction that it's hitting. So you're going to have a lot of canceling out sort of going, up and down in that type of regard. But because you're being pulled into a sphere, you're going to start to rotate around. And so the direction radially that you're going to go is not going to get canceled out. So everything's going to kind of get flattened down in that regard. You're going to end up with just that.
You observe lots of similar disks at different points in their evolution. Does that help you understand how?
Yeah, I would say that the specific class of Dipper stars that show these light curves like that are definitely pretty common. They're becoming more frequently studied now, but particularly for the reason that, maybe we can look at really young disks, we can look at really old disks, and if they all seem to show this pattern, what does that say about the planet formation process in general?
Question.
Yeah.
How do you find these dippers?
So finding these dippers is going to be primarily using some of these surveys that are here at the IfA. I think that this was first looked at actually in Assassin data. I don't think that they have a booth this year, but it's one of the IfA-based surveys. And essentially, just if you see an object that seems to be bright, bright, dim, bright, bright, dim, and if you just do a search for those within the data that you're able to collect, they pop out pretty clearly, pretty nicely.
And the fluctuations in the light or whatever could any of that be related to whatever light is being absorbed by that planet itself?
Yeah. So we did some follow-up work to try to check to see, is this a planet signal or is this the dust and gas and pre-planet material? And if it was a planet, we would expect it to orbit at roughly the same period. So we would see it every 7 days or whatever it is. And instead we see that this happens, even though it happens frequently, it doesn't happen at a very regular interval. And also the sort of depth of dips in the light curve that is caused is very variable. And if it was one object, we'd expect it to be maybe the same depth at each point because it's blocking the same amount of light. All right, thank you.
Alrighty. Thank you, Alexa. Hi, everybody. My name's Keyan Gootkin. I am a second-year graduate student here, about to, fingers crossed, get my master's. And I'm going to be talking to you all about a survey I did looking for Delta Scuti stars and specifically looking for stellar pulsations. But first off, I really just want to take a step back and give a little bit of context. As we think about what is a star, right? For most of human history, the vast majority of human history, since animals have had light sensing appendages and organs and whatnot, right? You look out at night and you see this spread of little dots in the sky, right? And for the most part, if you go out the next night, you look in the same spot, you'll see the same star, more or less. You go back for 100 years, see, it's about the same star. The stars are the same brightnesses. They're in roughly the same positions. And actually, this was sort of the basis for the beginnings of Western astronomy in ancient Greece. The Ptolemaic, the Aristotelian model thought of these as perfect pinpoints of light that were piercing the firmament. Now we know, right? This isn't really what's happening. Things are a lot more complicated. And actually, one of those base assumptions, right, that if you go out another night and look, you'll see the same star that's just as bright in the same position, is a pretty good assumption, but it's not perfect. So if you go around and you look at different stars across the night sky, eventually you'll find something like this star. You can see over the course of 2 days, it brightens and then slowly dims back down. These are really, really common. Most of the time, this is hard to see with the naked eye. So really, these were only discovered, these types of variability, we call it, within the past couple hundred years. The most famous and the type of variable star I'll be talking about are classical pulsators. Basically, they work just like a car engine, where right, you have a piston that goes down, and then the fuel explodes, sends the piston back up, it vents, and then starts the cycle over again. When you have a very specific temperature of star, you get a layer that works just like this. Instead of a piston, right, it's the whole layer of this star collapsing inwards. Instead of fuel exploding, it's actually trapping light. And so this light gets trapped, heats up the star, and causes it to expand. And this happens very regularly. For Cepheids, which is what this model here is, so the most famous type of classical pulsator, this is on the order of like days, so maybe 2 days, like the previous example. But this also goes down to of order hours. So over hours, an entire star will expand and contract, and expand and contract. And what's really, really important is that how long it takes for that star to do that contraction, what we call pulsation, depends just on how bright the star is, how much total light it produces. This is really important because this is really the basis of our understanding of the size of the universe. Back at the beginning of the 20th century, a human computer, Henrietta Swan Leavitt, it's what they called basically where they stuck the girls in the basement to do the calculations while the big boys upstairs did the, fancy thinking and writing equations. She is really an unsung hero of astronomy. She tabulated the brightnesses and positions of thousands of stars, and she discovered these Cepheids, these types of pulsators that have this very regular up and down motion, slowly brightening and dimming. And she was the one that discovered that it really just depended on how bright the star is. And what that does, right? Distances in astronomy are hard, right? You could have something like really dim, very close to you, or very, very bright, far away from you. And it's really hard to distinguish the two. So really, once you have, though, these stars where you can calculate just based on how often there's these fluctuations, how bright it is, you know how bright it should be, so that tells you exactly how far away it is. And that is what led Edwin Hubble in the 1930s to basically expand the scale of the universe that we know, right? He was the one to discover that the Andromeda galaxy was a whole separate galaxy, or at least to convince his contemporaries that that was the case. So, and this right goes on to the expansion of the universe. Really, everything that we know about cosmology today is because of classical pulsators, because of Edwin Hubble, because of Henrietta Swan Leavitt. And I'm this is part of why I'm very proud to join this legacy of looking at these types of stars. It's really rich history. A little more recent history, right? So I told you before that these stars, it happens when there's a very particular temperature, right? So that would be over here. And again, right, in science, we always start with the simple and then you poke holes in it, right? The stars are basically the same brightness whenever you look, but that's not quite true. And actually that not quite true thing leads us to the most interesting questions in science. So I told you before, pulsations happen when you're at a particular temperature. That means this line right here. So in this diagram, left is hot, right is cold. So this strip right here would be the temperature that corresponds to where you can get those pulsations to happen. Recent work, Murphy et al., 2019, took a really close look at this region, and in particular, the lowest brightness region. So up here are the Cepheids, but there's actually a smaller, much more numerous cousin that we call a delta Scuti, named after delta Scuti. We're very creative like that. But so Murphy et al. Looked at a bunch of delta Scutis all around the instability strip, this region where we should expect these pulsations to happen. And basically what they found is that we are missing stars. This plot here, the color represents what percentage of the stars in that area we find pulsations. And according to theory, if everything was working exactly how the models predict, this would be solid yellow, 100% inside the instability strip, and basically 0 outside of the instability strip. But that's not what we see. No matter how closely they looked, there were still regions right in the smack dab center of the instability strip where pulsations should happen, where they're missing. So this is where I come in. Basically, this used data from about 10,000 stars that they manually classified. That means looking individually at all of the observations and somebody deciding this is a delta Scuti star, this is some other kind of star, this is boring, this is nothing. But now, thanks to tests, we can do a little bit better. So how do we find a pulsator? Basically, just like Alexa was talking about before, you look at a light curve. So here I have 2 examples. On the top, you can see this is the light curve over 5 days of an eclipsing binary, right? So this is a star that has another star pass in front of it. And every time that the star passes in front of the other, the light, how bright the star appears, dips down because we're blocking some of that light. Whereas this down here is a delta Scuti. You might look and see, well, this is a really big signal and this looks like nothing, right? It looks like random scatter. What we do is we basically do what's called a Fourier transform, where you basically try and reconstruct this just out of a bunch of random little wiggles with different frequencies. And when you add up the wiggles with all the different frequencies, with all of these different frequencies here, you get something that looks like the original light curve. And this is really, really powerful. So you see here, this is an eclipsing binary with an orbital period of about a day. And you see over here, we see these big peaks that mean basically there's some weird signal out towards about once a day. Down here with the delta Scuti though, right here, it looks very unordered, very kind of random. By eye, you might not look like much, but here we see this huge peak right at about 13 times a day. So this is a delta Scuti star that is pulsating every about 2 hours. What you can do to make this look a little bit prettier, which is my main criterion when I'm doing science, obviously. Right, you basically, instead of plotting one point after another, every time that 2 hour period happens, you start over and you build up this one really clean, nice curve. So between looking at the light curve and these Fourier transform, these amplitude spectra, we're basically able to automate what had been astronomers handpicking stars. And that means that we can expand our search for these types of stars vastly. And we do that with TESS. TESS is a mission, the Transiting Exoplanet Survey Satellite, that basically every time in this GIF where something is added, that is a month's worth of observations, a month's worth of taking brightness measurements every half an hour. So every half an hour for a whole month, TESS looks at a part of the sky that gives you a month-long light curve, then it moves on to the next, and it's actually covered just about the whole sky. So now, instead of having to look at individual stars, instead of having to look at a particular part of the sky, we can look at the entire sky, all the bright stars in the sky, and try and figure out which ones are Delta Scutis, which ones are other weird types of pulsators, which ones are not pulsating and should, and try to figure out what the differences are between these groups. It's also just very pretty. And that, again, it always helps. And so what do we find? Well, we found a lot. It turns out that we were able to process and look through about the 1,000,000 brightest stars near to that strip in temperature where we expect pulsations. And what we get is something like this, where on the left, this is the Murphy et al. Paper from before, and here is our version. I wish I had made this a little bigger, but that's okay. Basically, right, you can see that over here, outside of the instability strip, it's about 0. To the blue side, it's about 0. And then you have this nice clean strip right here, where again, the maximum amount you get is something like 75% of the stars. So even with, right, we've increased the number of stars we're analyzing by 2 orders of magnitude, 100 times more stars, like the Murphy et al. Paper times 100, and still we don't see pulsations where we expect them. And furthermore, right, so what my research was trying to do was basically find this relationship again and basically provide a catalog to the community of all of these stars, these hundreds of thousands of stars, what all their properties are, and say, much in the way that, right, Henrietta Swan Leavitt sort of looked around and noticed a relationship, put that out there, and then was able to be turned into incredible scientific results many years later. We're hoping maybe some incredible scientists can do something to figure out what's going on at the center of this instability strip and why we're missing pulsators. It's a really interesting question that has really significant impacts on cosmology, stellar astrophysics, all the way down, really. And here, right, we see the period luminosity relationship, where along this line, we have all of our Delta Scuti classical pulsators, and we're able to actually fit a new line here, bring a new period luminosity relationship with the most stars that have ever been, anyone's ever attempted to do this with. And hopefully this is gonna make for a nice, fun publication. So thank you. I'd like to thank a lot of people. My mentors, Dan Huber, Mark Hahn, as well as Dan Hay, all of my fellow grad students, as well as my trusty assistant, Mr. Chupacabra Gootkin, who no doubt is very angry and hungry at home right now. So thank you. I'll take any questions.
What prevents the light from escaping?
Great question. It's a little complicated, which is to say, I mostly know how it works. But basically, in this specific layer, right, normally when you compress a gas, it heats up. And that, normally would prevent this sort of big instability from happening. But in this very specific layer, you get a partial ionization of helium, which is a fancy way of saying it knocks off some electrons from the atom. And so when you do that, instead of heating up the gas, it actually, that energy goes into ionizing kicking off electrons from this helium atom and increasing how opaque it is. So the star becomes less transparent. And so through that layer, it takes longer for light to travel through, just because the way that the helium atom works, it blocks more light, and then it all bounces around and gets trapped in there for longer. And the energy in there heats up the star, which then expands. And when it expands, it becomes more transparent and lets the light out. Does that kind of make sense? Me too. Me too. So, any other questions?
What do you think is the reason why you haven't found all the pulsators?
That's a good question. There's probably
Question?
right as why aren't we finding these pulsators? Right, the big question. Why is this 75% and not 100%? Part of it is likely due to limitations of our instruments, right? So how much the up and down wiggle right here is different for different stars. So if it's a really small difference, it's a lot harder for us to detect that with our telescopes. So some fraction, and that was sort of the hope, right, of answering this question as well. Theory is actually correct. We just need to build better telescopes. So right, one idea is we could just be not have enough sensitivity to detect those. But with the amount that we have, especially now with orders magnitude more, it seems there's probably some actual astrophysical, like structural reason in the star for these pulsations not happening. A couple reasons could be like binary companions. If you have another star right off the edge, then that sort of sends the whole system out of whack a little bit. There could be rotation. When you rotate a star, it mixes things up. And if you mix up all the different elements, you might not have the helium in that layer that you need to make that engine motion work. It could have, there could be, I mean, classic astronomer answer, maybe there's magnetic fields, which I don't really know how that would work, but I really don't know. And that's very exciting because, right, those are the kinds of questions where you really don't have a good answer, where there's probably some really interesting physics and some really interesting stellar astrophysics to do. So thank you.
Hello. There's not many people left in here. That's all right. I'm Chris. I'm a second-year grad student. The focus of my research is strong gravitational lensing. And so the point of this talk is less so to talk about my actual research and more so to talk about what strong lensing actually is. So you may have seen it. Produces these really beautiful images, but you may not know exactly what's happening here. And so I'm going to take you through kind of why you see what you're seeing here, like this galaxy in the middle and the ring around it. So I have to take you back a little bit and first explain a little bit about general relativity. So general relativity was proposed by Einstein in 1915. And so in it, it predicts that space-time is malleable and it can be distorted in the presence of mass. And so in the presence of large masses, you get really large distortions in space-time. And so as objects travel through this distorted space-time, it no longer travels straight, right? It's deflected. It travels a curved path through space-time. And so I was gonna plug the Spaceflight Lab demo. If you haven't checked it out, then you should. You can see it's a hands-on experience of what it's like to, or I guess it's a demonstration of the curved space-time and how masses can affect it and how things travel through that. And so, like I said, the sun is very massive, and the sun creates a large distortion in space-time. And so this man, Sir Arthur Eddington, went out to confirm the effects of general relativity by measuring the deflection of starlight during a solar eclipse. And so obviously when the sun is out, it's very bright, you can't see stars. And so during a solar eclipse, right, it gets quite dark and you can see some of the stars that are in the background at this time. And so Sir Arthur Eddington measured the position of these stars, and they were not where they usually are. And this is because the sun was deflecting them by some amount, an amount which was exactly what general relativity predicted. And so here's just a little cartoon diagram of what was happening, right? So you have the real location of the star, which is something like behind the sun. This is not to scale, by the way. The stars are much, much further away than this. But yeah, so you have the true position of a star, which is behind the sun, and the sun produces some deflection of that starlight, and it changes the apparent position. And so the sun is very massive, and it can produce this effect. There are more massive things in the universe, like galaxies. And so this galaxy in particular actually has the mass of about 1 trillion suns. And so this, as you can imagine, produces an extremely large distortion in space-time. And so just like the sun can deflect the light from a background star, galaxies like this one can deflect the light from other galaxies that are behind it. And so this is essentially what strong gravitational lensing is. And so it can produce effects which are noticeably different than just deflection of light, right? And so what happens in strong lensing actually is that not only do you have the deflection of light, but a galaxy in the background, which I've labeled as the source here, the light from it travels different paths through the gravitational potential through this distorted space-time. And so you can get multiple images of the same background galaxy. And not only do you get multiple images, but the light from this background galaxy is highly distorted and magnified, as I showed you here, right? You can see that, the galaxy that produces this arc-like shape is probably something that looks like this galaxy or this galaxy, except its light is traveling through this distorted space-time and it's being stretched and magnified into this arc. And so when you go home, you can actually reproduce this effect with just a wine glass. You can take the base of a wine glass and hold it up to a light source. And you can play around with it and change the angle and the distances, and you can produce an effect which is actually similar to gravitational lensing. So you can produce like multiple images, as you see here and here. It looks kind of similar to a real strong lens. And you can even produce rings, just the bottom left image there, just like the ring that I'd showed you in the previous slide. So that's a fun little take-home exercise for you guys. But yeah, so then this produces an effect that you see here, which I've shown you. And so, oops, sorry. This effect, I want to impress upon you that the fact that this is extraordinarily rare. So it's about 1 in every 10,000 galaxies can act as a strong lens. And so up until just a few years ago, we had only known about a few hundred strong lensing systems. And today we know a few thousand. And so a lot of the effort to discover these systems has been through surveys that are conducted here at UH. And in fact, that's something that I'm working on right now, is trying to look for more of these instances of strong lensing. And in fact, the man himself, Einstein, thought that we would never observe galaxy scale lensing. So basically what he says here in this quote from 1936 is that having this chance alignment of 2 galaxies is extraordinarily rare, so we should never see it. And also that our telescopes just aren't good enough to see it. Both of these things are not, well, the second thing definitely isn't true. The first thing is true, but because we have such amazing telescopes that can conduct surveys which cover large areas of the sky, it enables the discovery of a lot of these systems. And so with the discovery of a lot of these systems, it enables a lot of great science to be done. It also can produce a lot of pretty images. I'm going to skip that. Like this. So here you can see not just a single galaxy, but a group of galaxies. I guess the pointer is probably better to use here. This one, yeah. So you can see all of these yellow galaxies, these round yellow galaxies in the foreground. They are, sitting there. They're all in a group with each other, and they're just creating this distortion in space-time. And this arc that you're seeing here, and this image here, are of a background galaxy. And so you can see it being highly distorted and magnified in this arc. But what's very interesting about this particular example is that you have an image of the galaxy which is mostly preserved. So you can actually make out structure in it. It's actually a spiral galaxy. You can see here's the core of the galaxy and some spiral arms, right? And in this arc, you can see that galaxy again, right? There's the core, maybe there's a spiral arm, right? But it's highly distorted into this arc-like shape. And so you can get other kind of configurations for strong lensing. So in this case, you have again a group of these yellow galaxies. And in this instance, you don't only have one galaxy that sits behind it and is being lensed. You actually have 3 different galaxies that are being lensed and multiply imaged. And this is quite a rare occurrence. And you can bump the scales up even more, right? So you have some of the most massive clusters of galaxies, which contain tens, hundreds of thousands of galaxies, creating, some extraordinarily large distortions in space-time. And, as you increase the size, you also increase the potential for, other galaxies to sit behind, a cluster like you're seeing here. And so you can get like tens of arcs. Every little streak of light that you see is another background galaxy which is being strongly lensed. And I have a few more examples of this. Here's one, right? You can point out some of the major arcs here and here, right? And you can have some incredible images like this. Again, this is called the dragon. So you have an arc like this, right? Where you have a very distorted image of the background galaxy and then an image of it, which is somewhat preserved. You can make out some of the spiral structure in that galaxy. And so this is why strong lensing can really act as a sort of cosmic telescope. So this magnification of the light from background galaxies enables us to study galaxies which are very, very distant, that we would have otherwise not been able to observe. And so these galaxies sit billions of light years away, have formed something like, a few billion years after the universe, after the Big Bang, right? The universe is only a few billion years old. And so studying galaxies at this time is really important for understanding the evolution of the universe and how galaxies formed and how they evolved into the present day. Right, so this is just one scientific pursuit of strong lensing. And so something that I've kind of been keeping secret this whole time is that everything that you see in this cluster is only about 20% of all the matter that's actually there. So there's this thing called dark matter. You may have heard of it. It's called dark matter because we don't know what it is. That's the classic line. So stars and galaxies and dust and gas only make up about 20% of the matter. It makes up 100% of the matter that we see, but only 20% of what's actually there. And so this dark matter plays a key role in contributing to this lensing effect, right? Because it's extremely massive. There's a lot of it, right? And so the thing about dark matter, the reason why we don't really know what it is because we can't see it, it's invisible, and it doesn't interact with normal matter. And so the only way that we can, observe its effects is through, the only way we can observe it is through its gravitational effects, right? And that's why strong lensing is the most powerful probe of dark matter that we have in the universe, right? Because if we can model systems like this, right? So again, you see some foreground galaxies and some lensed arcs. If we can model systems like this, then we can model the dark matter that's within them, right? You can model the distribution of dark matter, and we can also determine how much dark matter there is in galaxy clusters like this. And again, this is, through gravitational lensing, it's one of the few ways that we actually can study dark matter, because direct detection of dark matter, like the particles, have so far been unsuccessful. And so that's kind of where I'm going to wrap up my talk. But there are many other things that I haven't talked about here. So we did talk about galaxy evolution, understanding galaxy evolution through the lensed galaxies, and we've also talked a little bit about dark matter. But there are many other things that I haven't, and so I like to view strong lensing as kind of this unique tool that we can use to study the universe, and it gives us insight into a lot of things that we otherwise wouldn't be able to understand. And so, I'm going to continue to do my research with strong lensing. And so hopefully I can uncover, some more secrets of the universe that, that we don't yet understand. Thank you.
How do you find a lens? Like, how do you tell the difference between a kind of just wonky looking galaxy and something that is actually being lensed?
Yeah, so The main thing is through spectra. So right, spectra, when you can break up light into smaller bins, and so you can determine how far away these galaxies are, and so like we know that all of these yellow galaxies that we see are like a lot closer to us than a lot of these background galaxies are. But also morphologically, you're just not able to produce like the arcs that you're seeing in this image through any other astrophysical phenomenon. There are some instances where you have much lower resolution data where it's a bit more ambiguous. So you don't know, maybe you have like a galaxy merger and you have some long like tidal tail where a bunch of stars are tossed out. But when you get high resolution imaging like through Hubble or on telescopes of Mauna Kea like Keck, then it becomes pretty clear what we are looking at. So like I said, a lot of the lenses are being discovered in ground-based surveys because they cover a large area of the sky. But we like to only call those candidates until they either receive spectroscopic follow-up or high-resolution imaging follow-up, in which we can confirm that they are in fact lensing systems.
Does the lensing switch the frequency of the light that you see, or?
Yeah, that's a great question. So lensing is monochromatic, which means it affects light no matter where you are in the electromagnetic spectrum. It affects it all the same. So like the colors that you're seeing are the true colors, right? It's not like a lot of other like lenses, right? A lot of other lenses are achromatic, or they deflect light by different amounts at different wavelengths, different colors, but that is not the case here.
Okay.
Yeah, so that's a big thing that
It's gravitational warping rather than optical warping.
Yeah, so it's you don't actually have a lens, right? A physical lens, and
Yeah.
so the physical lens is what causes this achromatic lensing. But yeah, here it's just a deflection, not through like a different medium, but you're just like that. I think that's the key point, is the light is not traveling through a different medium. Light, you're not traveling through a lens or through something else. It's just being deflected. So that's where it differs from actual physical lenses.
Is there a delay associated with that? Because if there's so do you have to look at this image, this lensed image at a different time as you're looking at the original source to compare it?
Yeah, that is an excellent question. That is one of the big things that I didn't talk about. So if I go to a more simple system, maybe this guy's clear. So here it is clear that you have a galaxy which is being imaged 3 times, right? You can see it in the cores. You can see the core of the galaxy 3 times. And so for each of these 3 images, the light from the background galaxy is taking different paths through this distorted space-time. And so you have a finite speed of light, right? And this means that the light arrival time to us is different for each of these 3 images. And so, Keyan was talking a bit about like how measuring distances, can get you, can answer some of your cosmological questions. Basically, if you can measure the delay in arrival time from each of these images, then you can measure the expansion rate of the universe. So that is something that I'm also working on. This is typically measured through, if you have time variable sources, then you can measure the time delays. So for instance, supernovae, exploding stars, but those are extremely rare, right? You have supernovae are rare, lensing is rare, so lens supernovae is even rarer. But yeah, that's a great question.
How big is the time delay?
Yeah, it depends. So typically the size of the system tells you about what your time delay should be, right? So for so this is a single galaxy acting as a lens, so it's quite a bit smaller than some of the big cluster systems that I showed you. And so I would expect you can actually see 1 image, 2 images, 3, and then I think this one is the 4th. So for a system like this on this scale, like single galaxy lenses, to expect the time delay to be anywhere from a few days to a few months. But for cluster systems, not this one, oops. For cluster systems, something like this, you can expect, it's not clear that you can't clearly see multiple images, maybe here. Yeah, so like this arc has 2 images here. For systems like this, with a much larger potential, much larger distortion in space-time, and a much, well, I said it, much larger deflection, then your time delays can grow significantly. So they can be on the order of months, years, even decades. So in fact, there was a lens supernova that was found in a cluster which is much smaller than this. And the time delay that was measured there, or predicted there, it's not yet measured, is about 10 years. And so, set your calendars, come back in 10 years, and maybe.
Some of that related to how far away that light is, or by the lensing?
It is all due to the lensing effect. Yeah. So the further away something is, there's actually a different effect, which is called time dilation. And so basically, the further away something is, because of the expansion of the universe, the longer it appears to be. So like if you have a supernova, which is going off much, much further away, like somewhere far away in the universe, you can expect the time that it takes to rise and fall can be stretched out. So yeah, that's time dilation, which is a different effect. Yeah. Now I know why everybody left. Thank you. Thank you for your questions. They were great.